Welcome to AP Chemistry at Heinig High School. I'm BBrown, and today we'll be looking at our second part of notes dealing with titrations. So this is really the second part of section 17.3, dealing with the titrations of weak acids and bases versus strong acids or bases. So before we looked at strong titrations, and remember when we saw a solubility or a titration curve for strong, a couple of points of interest when we had our titration curve is we would see a curve that looks something like this. And within that curve, there are a few points of interest that you had to understand. I said first you need to understand and evaluate this means down here. It means we're basically starting with an acid, and because of how it's increasing, a steady increase like that, that tells me that that's a strong acid. So we're titrating a strong acid, and then over here, since once again we've got a steady increase situation, that would be a strong base. So we're titrating a strong acid with a strong base. So that's one thing you should be able to look at. It's the beginning and the end. If it's got a gradual increase in each of those spots, then we know it's a strong situation. And as a strong, we know the equivalence point, which basically you look here and find that middle point there. You know that that's got to be pH 7 when we're dealing strong. So that's another dead giveaway that you got a titration of a strong with a strong. And then the other point of interest on here that is useful would be, because this is going to be the volume of our base, in this case probably something like NaOH as a strong base. So what volume that is at our equivalence point is going to establish what our OH minus concentration is, which tells us what our H plus concentration is. And if we knew the volume of our acid, we could divide those and get the concentration of our strong acid. So those are the major points of interest in a strong situation. Well, when you look at a weak strong situation, it looks very similar. You have this S-shaped curve. You have a spot right here that in between that we're going to have our equivalence point. But notice instead of being at pH 7, now we're not at pH 7 anymore. And that's one of the common misconceptions coming from pre-AP is most students think in a neutralization reaction at the equivalence point it's going to be true neutral, pH 7.0. Well, that's because there's something a little bit different happening with a weak acid titration against a strong base than our strong situation. In the strong situation at the equivalence point, H plus equaled OH minus. Well, that made water and some salt, and it was a salt of two strongs, so like sodium hydroxide and hydrochloric acid would give us NaCl. Well, the salt made up of two strong conjugates is going to be negligible. So at this point we truly are at pH 7. We have pure water with nothing to affect the acidity. That's not going to be the case in a weak acid titration. So that's one dead giveaway. You should notice that the equivalence point we're not at pH 7 anymore. But what that pH is, and then going down what that concentration is, those are two important things on this graph. Now, another important thing on this graph is I see at the end here that gradual increase. That tells me strong, and since I'm on the base region, that means I'm titrating with a strong base here. And since I'm starting below pH 7, I know I'm starting with an acid, but notice it's not a gradual increase. It has this little hump at the beginning. That's your dead giveaway that you've got a weak. So what we're titrating here is a weak acid against a strong base. So there's a couple of points of interest that are similar but different to what we talked about before with the strong. So you should be able to look at this graph and figure out a few things. Now with weaks, there's one other thing on here we're going to end up talking about. But how does it tail at the beginning and the end? That tells us strong versus weak. And where's our equivalence point? How do we find that? How much acid or base was added at that point to get to the equivalence point? And then what actually is the pH at that equivalence point? Remember, if it's not at 7, then you don't have a strong situation. Now, unlike in the previous case, the conjugate base of the acid affects pH. When we had a weak acid, it was becoming a neutral salt. The conjugate of strong is negligible. So the conjugates that we got from our strong acid and our strong base were negligible in acid-base behavior. That is no longer true, and that is a huge difference between what we looked at before and what we're looking at today. So in this particular case, when we have some weak acid, it's going to disassociate into a conjugate that is not negligible. This thing is going to be a weak base. And that ends up affecting the whole pH issue. So unlike before, the conjugate of our acid here is going to have an effect on the pH when it gets formed. That's something that is different from before. Before we never worried about what the conjugates were because they were negligible conjugates because they were coming from strongs. Now, at the equivalence point in this particular reaction, a weak acid versus a strong base, notice the pH is greater than 7. That's always going to be the case with a weak acid versus a strong base. The pH is going to be greater than 7. So this tells you it's a weak acid against a strong base. So that's what that means. If your pH was less than 7, that would tell you it's a weak base being titrated with a strong acid. Why that ends up happening will make sense when we really get into what species we have at the different points of the titration here. So why does that happen? Well, phenolphthalein, actually this is kind of off the topic here. The why is a different idea here. One of the things I want to look at related to this is at the equivalence point, since our pH is greater than 7, remember when we pick a indicator to tell us when we're at the equivalence point, so we want our end point where it changes colors and tells us to stop the titration, we want the end point to match our equivalence point. In this particular case, since our pH is greater than 7, something like methyl red, it's changing colors while we're still increasing before we're at the equivalence point. So phenolphthalein would be a good indicator. That's what this is talking about here. So phenolphthalein is basically our indicator. Now, the thing that was up there a second ago, why is it that we end up with a pH greater than 7 here? Well, take a look at what's happening in this reaction. We have our weak acid at the beginning here, and then as we start adding our strong base to it, now remember our weak acid is going to be reacting with a strong base like NaOH through a neutralization reaction. Well, when this OH minus, because our Na basically is negligible, so what we're really doing here of importance is adding OH minus. When we react an acid with OH minus as a weak acid, remember that's going to be an HA type situation, we're going to end up making water. So we're neutralizing that weak acid with the OH minus, but what's left over, this A minus, is a conjugate base of a weak acid, which means it affects our pH. So at neutralization, yes, our acids and our bases cancel each other, and we've gone to water from them, but we have a whole bunch of this A minus in there, and that A minus is a weak base. Well, that's going to make it slightly basic. So the answer to our why is because we make this conjugate base that affects the acidity. In this case, it's a conjugate base of a weak acid, so it's going to be basic, and that makes our pH greater than 7. And that's why when we look at a weak base reaction, when it gets neutralized, we're going to have its conjugate acid, which is a weak acid, but it's still acidic. It still affects the pH. So that's going to make our pH below 7 at equivalence point in that particular situation. So we've got different things happening here with weak acids than we had with strong situations. Now at the start, pH is determined by the concentration of the weak acid. Now before, when it was strong acids dissociate 100%, so the concentration of acid was used to get the concentration of H+, and we just take the negative log of that to find our pH. Well, when we have a weak acid, it doesn't dissociate 100%. So what we really have to do is look at that acid at the beginning, because there is no base added to it, and we're going to find the pH just like we do any weak acid reaction. We need to know what the concentration of the HA is, we need to know what the Ka is, and we set up that reaction. Ka equals x squared over our HA concentration minus x. Just like always, we neglect x here, and we find out what x is, and x is going to represent our H+ concentration. And then we can take the negative log of that. But this is very different from what we did with strong. And it's a little bit more involved. That's why this stuff is a little bit more in-depth than what we looked at with strong. So the notes there were much shorter than what we're probably going to see here. So that's what we have at the beginning, is basically our normal Ka situation. We've got a weak acid, we haven't done anything to it. Once it's H+, that's just like last chapter. The second thing second region of our graph here is this region before the equivalence point. So in this region, what's happening? Well, our pH is changing here, and that's because we've neutralized our weak acid a little bit, and that's going to have an effect on our overall pH. So between the initial pH and the equivalence point, you have a partial neutralization that's going to create a buffer. So what we're really doing here is buffer math, just like we did yesterday. I should say 2 days ago. So what we're looking at here is, and you can do this with Henderson-Hasselbalch, you can do this with the acid reaction we looked at that's derived from the Ka expression. So remember, we can take Ka, which is going to equal H plus times A minus concentrations over HA. And we can use this and solve for H plus, which means we basically have to know what is my new concentration of my acid after I've partially neutralized it, and what is my new concentration of my base after I've created some. Because remember, what happens here in this reaction is HA is going to make H plus and A minus. As we continue to use up HA, we make more A minus. So we make our conjugate base from our conjugate acid. So this is very, very similar. In fact, it's identical to what we did with our buffer math type situation. We took a look at what was the concentration of my acid and what was the concentration of my conjugate base, and we use Henderson-Hasselbalch or the above equation to calculate what that's going to do to the H plus concentration or the pH. So when we are doing a weak acid titration before the equivalence point, we're in the land of buffer, which means you have to do buffer calculations. So you're going to find HA and A minus. And remember, it's straight stoichiometry neutralization. So for every 0.1 moles of OH minus we add to HA, that's going to lower the number of moles of HA by that exact amount. And that's going to raise the value of A minus by that exact amount. So remember, every bit of this that leaves becomes that. So you set up a simple, what is my HA concentration, what is my OH, or what is my HA moles? So really you're looking at the moles of H plus. What are the moles of OH minus I'm adding to it? And for every amount of OH minus you decrease the HA moles, you're going to increase the A minus moles. Dividing by the total volume that exists inside there, you will get the concentration of each. So remember, what you're really going to do here is probably Henderson-Hasselbalch or the acid equation that can be derived up top for H plus as it relates to Ka. So in region 2 here, you're going to be doing buffer math is really what it comes down to. Now in region 2, there's something else. I mentioned when we do weak acids, there's some differences between weak strong and strong strong. Another really important difference is what's called the half equivalence point. And this is unique to weak acid titrations or weak base titrations against its opposite. And what basically the equivalence point is, and this comes right out of Henderson-Hasselbalch. Remember, we use up our acid, so this is going down by some amount, and that creates our base, its conjugate, and that goes up by some amount. Well, when we have taken, let's say we had an acid mole amount of 8. When we cut it in half by adding 4 moles of OH minus, we're going to be down to 4 moles here. And the difference between these two is exactly how much A minus was created. So what we have here is a buffer situation. I'm going to have 4 moles of my acid left, and I'm going to have made 4 moles of its conjugate A minus. So what we've done is we created a buffer. Well, at the half equivalence point, we've cut this in half. These two are equal to each other. This is an equimolar situation, which means this is log of 1. Log of 1 is 0. So what we have is pH equals pKa. So whenever you look at an acid-base titration of a weak acid or base, there's a really important thing that you need to understand, you can derive from that graph, that most of the people taking the AP test are going to be clueless about. So the half equivalence point is really important. So how do you find that? Well, here's my equivalence point. Remember, I look at where that is, cut that in half, that's my equivalence point. If I go straight down, that would be what my base amount was at the equivalence point. Half of that, I will have half neutralized the acid. So I go to the half equivalence situation. So in this case, it's going to be 25. And then look at what that pH is. The pH at this point, which is around 5, probably just a tiny bit below it, but it's around 5, is going to equal my pKa. Well, if I know the pKa is 5, 10 to the negative fifth would tell me my Ka. So what you can do from this graph is you can determine the Ka of the acid. So one of the things that most people miss on the AP test, when you're given one of these diagrams, a valid question would be, and this could be easily on the multiple choice portion where you don't get access to your calculator, what is the Ka of this weak acid? Well, most people look at that and have no idea. Remember, we look at the halfway point, and that means at the halfway point, what was my pH? A little less than 5. So I think, okay, 10 to the negative fifth is what it would be if it was 5. So that's going to give me 1 times 10 to the negative fifth. If I'm a little bit below that, I'm going to be in the upper range of the 10 to the negative 4. So I would say somewhere probably in the 7 to 9 range times 10 to the negative 4 would be what my Ka is. So remember, the half equivalence point, a really important point. So to review what you're supposed to get from this graph, we're supposed to be able to determine weak acid from that, weak acid from that. Both of those things tell me weak acid because the pH is above 7 at the equivalence point, and I've got that little loop instead of a steady uphill. I've got a steady uphill at the end that tells me strong base. I know how much base it took to neutralize, so I could calculate the number of moles of OH minus it would take to neutralize that weak acid. And I know, because of the half equivalence point, what the pKa and Ka is. So all those things come off of that graph. So there's a number of things you should be able to get from that graph. So, important thing really happening here in region 2. Region 3, we are at the equivalence point. Now remember, that's when H plus and OH minus neutralize each other, which would normally give us a pH of 7, except for the fact that we have created the weak base, A minus, which causes our solution to be slightly basic. So when you have a weak acid, your pH is going to be above 7. Now, how do you actually calculate what it is? Well, remember, the acid-base stuff from the weak acid and the base that we're titrating with, they're going to cancel each other, so they're irrelevant. What really becomes relevant is we have made the conjugate of our acid, so our Ka reaction, if we take the conjugate of that reaction, which is going to be A minus, so the Kb of the A minus reaction, so A minus reacting with water to make OH minus and HA. Oops. Let me clean that up. That should really be OH minus there. So that's a base reaction. We're looking at the conjugate being in water, and this is conjugate in water. So what we really need to know is the Kb of A minus. And remember, we get that from the Ka of the acid that we've got, divided into 1 times 10 to the 14th, and we can use that to calculate our pH. So we're basically looking at what is this thing. So we're looking at that reaction because we've got Kb. So what's the concentration of A minus? We use the Kb and that in a normal icebox problem to calculate the concentration of OH minus. And from there we can get POH, which gives us pH. So this is a problem very, very similar to the one that we did in the land of buffer before. It's the same Ka expression, but now it's going to be a Kb expression. So at the equivalence point, you're basically looking at using the Kb of the conjugate of the weak acid to determine what the pH is going to be. Beyond the equivalence point, now we're going to be in the land basically of the strong base. We've gotten rid of all of our weak acid. We've gotten rid of all the buffer situations. And what we really have here is a whole bunch of OH minus. So we take a look at how many moles of OH minus we have added at this point. And remember, you can get that from your graph here. So at this particular point, I've got that volume, and I know its concentration, so I can calculate how many moles of NaOH, which tells me how many moles of OH minus. Well, by the concentration of the weak acid, I can find out how much H plus that weak acid has, subtract the 2, and that tells me how much OH minus is left. So basically, up until the equivalence point, we were using up all of our OH minus, so it didn't exist. After the equivalence point, now it's all about OH minus. So subtract out how much H plus we had from our weak acid from how much OH minus we've added. Divide by, once again, remember, really important, total volume. And remember, we're dealing with OH here, so this is going to give us POH if we take the negative log of it, so we have to subtract from 14. Now, choosing indicators. Because you're not at 7 anymore, the same indicator used for a strong reaction might not work anymore. In our strong situation, it kind of went like this. So both methyl red and phenolphthalein worked equally well because they both changed colors in the range of where the equivalence point was. But now that we've got a weak situation, you can see that not every indicator is going to work. Phenolphthalein still works fine, but methyl red is no longer going to be an acceptable option here. So since at equivalence we're going to be slightly basic, phenolphthalein is going to end up in the right range, but methyl red won't work. So what do? Well, if you've got your titration curve and you take a look at what indicators, so I'm just going to lay some indicator colors over that I've matched up the pH scale here. So this was my original pH scale of my indicators, so that 2s kind of match up here and 4s kind of match up and 6 kind of match up. And you can see in this range, it looks like this would be fine, this would be fine, this, maybe when it goes from yellow to orange, that would be about right, so that one's kind of iffy. And then this one too, kind of iffy. If it was green when it truly went to blue, that would work, but those are probably hard to tell. So realistically, what are going to work best? Based upon this pH, this substance, which is our phenolphthalein, we mentioned that ago, and this substance, which is going to be thymol blue. But it's not when the thymol blue goes from red to yellow, it's when it goes from yellow to blue. So once we get to blue, we would stop. So we've got a couple of different indicators we can use. So you really need to match your indicator to where it changes color versus the equivalence point. Now, a really important factor, so another way to look at this, is to have data like this. So if I know the pKa of my indicator, indicators are weak acids. So the pKa of the indicator is known as pKIND. If we take a look at what the pK of the indicator is, and we compare that to the pH of our equivalence point, we can decide what would be an appropriate indicator. So methyl red changes, its pKa is 5.1. So if 5.1 is very near our equivalence point, methyl red would be a great indicator to use. So you can also use the pKa's of the acid rather than just look at where the color changes end up. So what you're really doing is the pKa of the indicator needs to be equivalent to the pH at the equivalence point. So that's really what we're doing here, is looking for that. So if we have this graph situation, now remember, a couple things we're supposed to know. It doesn't go straight up, it's got a little lip here. It tells me weak acid. Go straight at the end, that tells me I'm titrating my weak acid, with a strong base. So let me change colors on that. That tells me strong base at the end there. Here seems to be the range of where we were going straight, so halfway in between. It looks like we're going to be right around 8 here. So somewhere in the ballpark of 8 is really where our equivalence point is going to be. Well, look at your values up here. Which one has a pKa of around 8? Right there. Phenol red would be a great indicator. So another thing to use is to remember that the pKa of the indicator should equal the pH at the equivalence point for our indicator. Now, if we're doing a weak acid with a strong base problem, then what you really have to do is break it down into which of the 4 regions are we at. So you're either at the start, that's an icebox Ka problem, so you need to know the HA concentration, and you know need to know the Ka of the acid to calculate what your H plus is. That's because we haven't added any OH minus yet. Now in region 2, we're before the equivalence point. H plus is going to be greater than the OH minus. So what we need to do here is basically determine what the concentration of our acid is, HA, and what the concentration is of our base, A minus, and do a Henderson-Hasselbalch. So if we know the Ka, we can find the pKa, and we can add to that the log of the concentration of the base over the concentration of the acid to calculate what our pH is. So in region 2, think Henderson-Hasselbalch, H squared. Region 3, we're at the equivalence point. Normally that would mean H plus equals OH minus, they're neutral, the salt's neutral, pH 7. But in this case, we have made a conjugate base. So you're going to use the Kb and that base reaction to determine X, which is going to give you OH minus, which we can use to find H plus. So that's what you're going to do in this region, is you're going to do the Kb. So remember, this was Henderson-Hasselbalch, and you needed to know these two things. And at equivalence, doesn't really matter about the weak acid or the base we added. It's really all about the conjugate base. So you're looking at the conjugate base. Set up your normal solve for X, but that's going to give you OH minus. And then finally at the end, OH dominates. So find out how much OH minus the base has contributed and subtract from that how much H plus the base was. That's your concentration of OH minus. Take the negative log of that and subtract from 14. So you need to understand where you're at, which means you need to find and know where this thing is, because this is easy. And if we know where this is, and I've got a lower volume, that means I'm here. If I've got a higher volume of my base, that means I'm here. So it's all about really establishing where the equivalence point is. So look on your titration curve, if they're giving you a titration curve, and go down to see how many mole or milliliters of NaOH have to be added for the equivalence point. If we've added less, we're in region 2. If we've added more, we're in region 4. Now, titration of a weak acid with a strong base. Other ideas. With weaker acids, the initial pH is going to be higher. Remember, with a weak acid, it's not as acidic, so it's going to end up with a higher and higher and higher starting point. And it's going to also get rid of our nice, beautiful equivalence point. It's going to make it more subtle. So when you have a stronger weak acid, you get a easier to find equivalence point because it lasts for longer. But as we're getting weaker and weaker acids, our equivalence point region gets harder and harder to find. So like somewhere in, with this, we've got to look at, this region, it's easy. We look at that overall range, and yeah, we can say the equivalence point, bam. But when we get less and less room here, it gets harder and harder and harder to see where the equivalence point is. It shrinks down into, in this blue one here, we really have to kind of estimate and say, it looks like right around there. That's kind of my halfway in between point. And go over there and go down there. So the equivalence point gets more subtle to find as you have a weaker weak acid. Oh, and another mention here, and notice what's going to happen. If we have a weaker weak acid, we're going to have a stronger conjugate base. So we're getting farther and farther away from 7 at our equivalence point. It's getting higher and higher and higher. So 7 is kind of the minimum for a weak acid. And the closer we get to a strong acid, the closer we're going to get to 7. The weaker the acid gets, the more we're going to get away from 7. So the initial pH is going to be higher, and the pH near the equivalent point is going to be much more subtle when you have a weaker weak acid. Now, a weak base with a strong acid. Notice we're starting now on the other side. So I'm starting up here in base, so I know I've got a base. This would be what the strong base looks like. This little loop here would be what the weak base looks like. So remember, we can use that right away to see which situation we have. And notice, with our weak base situation, where the equivalence point's at is no longer at 7 compared to where it was here, which is going to be right at 7. So strong, still at 7. We're just coming at 7 from a different point of view, lowering the pH to get there. But if we have a weak base situation, remember, pH is going to be farther away from 7. And remember, the weaker the weak base is, the closer to 7 our starting point is going to be here, and the more subtle and harder it is going to be to find our equivalence point. The stronger the weak base is, the easier it is to find equivalence point, and the lower away from 7 its conjugate acid is going to be. So at the equivalence point, these titrations are always going to be less than 7. So something like methyl red would work better here than phenolphthalein. Phenolphthalein worked great for our weak acid titration, but not so well for our weak base titration. Now, if you want to do the math here, it's the exact same thing. Remember, at the beginning, you're going to have no H plus, so it's going to all be OH minus. Find POH, subtract from 14 to get pH. And know where this is. If you've added less acid than that volume at the equivalence point, you're in region 2. And now you're doing basically the opposite of what we did before. We did Henderson-Hasselbalch the acid form, now we're going to use the base form of Henderson-Hasselbalch. So we basically need to know what our weak base is and what its conjugate acid concentration is, plug it into the base form of Henderson-Hasselbalch to find our POH, and then from that we can subtract 14 to get pH. If we've got more or a greater volume of acid than the equivalence point, then it's going to all be about what is the number of moles of this that we currently have, and then subtract out the number of moles of OH minus that we got from our weak base. And remember, that's not going to change. This is going to be a constant. What's going to happen is, as we go up, this is going to be getting greater and greater and greater. So we're going to be getting more and more and more acidic. Makes sense. Next thing from this section you should understand, if you look at a titration curve and it looks goofy like this, it means it's polyprotic. And since I see two endpoints, that means this would be the endpoint of my first reaction dealing with the Ka1, the first hydrogen coming off. So that would be the equivalence point of the first acid reaction. And then over here we have another equivalence point region. That would be the equivalence point of my Ka2, the second hydrogen coming off. So if you see two flat regions in the S curve, that means you had a diprotic acid. If you saw three, it would be a triprotic acid. And once again, there's information that these things give you. You can find out really what your concentration is at the first equivalence point and the concentration at the second equivalence point. And you can find their pHs at each of those areas too. So there's a number of bits of information we can get. But that's what, you won't have to do a math problem with polyprotics, but you might be given a curve and know, oh, it's got two equivalence points, that's got to be a diprotic acid. And that finishes our second set of notes over section 17.3.